Picture a kid out in the yard just learning to throw a baseball at a target. That first throw, it misses completely, maybe hits the fence. The second throw, still a miss, but a little bit closer. By the third or fourth throw, they're actually zeroing in on it. Now, we aren't just watching a backyard game here. We are literally watching the birth of intelligence. It's not magic, it's a beautifully structured process. And that brings up a really profound question. How does improvement actually happen? Think about it. How do human beings, athletes or musicians, manage to refine their skills over time? A musician plays a chord, hears a slightly sharp note, and instinctively adjusts their finger pressure on the string. A chef tastes a sauce, realizes it's bland, and throws in a pinch of salt. They take in reality, feel the gap between what they wanted and what actually happened, and they make an adjustment. Now, let's pivot for a second. How does a machine do this? How does an AI model make that exact same journey toward improvement? We constantly hear all these heavy buzzwords, right? Neural networks, transformers, gradient descent, and it makes us assume AI is some kind of incomprehensible, magical black box. But underneath every single complex AI system out there is something surprisingly simple, something deeply, almost shockingly human. Every improvement begins with a mistake. Seriously, mistakes are not something to be feared or avoided. In the architecture of intelligence, being wrong is the absolute foundation of all learning. Before a machine can ever learn a single thing, it must make an error.
Part 1. Improvement begins with mistakes. You see, our world is never static. Weather patterns shift, water levels rise, stock prices bounce around. To learn anything at all, we first have to be able to measure that change. We don't start with complex formulas. We start with real life. Because if we can't measure how things are changing, we have no way to measure our mistakes. Just look at this striking mirror between us and the machine. Think about human practice. You take a shot and see a miss, you feel the error, and you adjust your aim. Now look at machine learning. A forward pass makes a guess, a loss function measures the exact size of the error, and gradient descent adjusts the aim. Physical reality and machine algorithms are both running on the exact same loop: input, attempt, feedback, adjustment. Part 2. Measuring change and sensitivity. Some changes are incredibly slow, while others are blazingly fast. Imagine walking up a really steep, short staircase versus strolling up a long, gentle wheelchair ramp. Your body feels that steepness, right? Well, in mathematics, that physical sense of steepness becomes what we call slope. Slope is simply our first careful way of measuring exactly how fast or slow a change is happening. But what if we could freeze time? What if you could measure that change at a single exact fraction of a second? Like glancing at the speedometer in your car or gently turning the volume dial on your radio. A derivative is just that. It's local sensitivity. It just asks, hey, if I nudge this dial a tiny bit, how much does the volume respond? Asking that question creates sensitivity. Sensitivity becomes the derivative. And that derivative? That becomes learning. Part 3. The machine's pain signal. When a student bombs a math test or a basketball player airballs a three-pointer, they feel disappointment. It physically stings. But a machine can't feel disappointment. It doesn't have an ego. So, a mistake has to be quantified into a hard, solid number before a machine can reliably do anything to correct it. We humans call it a mistake. Machines call it loss. And let me tell you, this is a massive shift in how we think about the problem. Loss measures exactly how wrong a prediction is. It acts as a single glaring signal that tells the AI whether its overall wrongness has gone up or down. It literally translates a real-world miss into a number that the computer can hunt down and fix. But here's the catch. Different mistakes require different measurements. If we look at absolute error, we're really just taking a tape measure to the raw size of a mistake. But if we look at squared error, something absolutely fascinating happens. By squaring the distance of the miss, a massive error suddenly becomes a giant, screaming penalty. This gives the AI a really smooth, distinct signal telling it to urgently fix its most embarrassing, biggest errors first. Part 4. Descending the foggy mountain. I want you to imagine a hiker who's totally lost on a mountain, wrapped in super thick fog. They're trying to get back down to the valley floor, but they literally cannot see the bottom. They can only feel the angle of the ground directly underneath their boots. So how on earth do they get down? Simple. They feel the slope, they take one careful step downhill, and then they check their footing again. If a single derivative is just one knob on a radio, a gradient is like the control board in a massive theater lighting booth, with hundreds of sliders being perfectly adjusted together to set the scene. It collects the sensitivity across all the different weights. The gradient is essentially a directional map that points downhill. It tells the machine exactly which combination of microscopic moves will reduce the most error. And that brings us to gradient descent. People use this term all the time to sound smart, but it's not some mysterious ancient intelligence ritual. It's just repeated local correction. Feel the slope. Choose a careful step size so you don't accidentally jump off a cliff and overshoot the valley. And measure again. The AI is literally just taking small, careful steps downhill in the fog to find the absolute best solution.
Part 5. The path to optimization. Real improvement almost never arrives as one giant cinematic leap. Whether you're an Olympic athlete training, an artist sketching, or someone trying to learn French, true mastery arrives as tiny corrections. Thousands or even millions of tiny, almost imperceptible corrections repeated over and over and over. Which builds the first half of what I like to call our central staircase. Every journey begins with a guess. That guess inevitably leads to a mistake. We take a measurement of that mistake, which gives us our loss. We test the sensitivity of that loss, which creates our gradient. You see what just happened? A clumsy real-world mistake has now been transformed into a tangible, actionable, mathematical signal. And that sets up the second half of our staircase. That gradient directly points the way to a correction. The correction naturally leads to an improvement. When we loop this process a million times to find the absolute best possible outcome, we call that optimization. And repeated optimization, that is literally the exact definition of learning. Part 6. How artificial intelligence learns. We can see this whole staircase inside a single artificial neuron, the absolute smallest decision unit inside an AI. Raw information enters as an input. It gets assigned an importance level by a weight, shifted a bit by a starting tendency called a bias, and then it spits out an output. It's basically a microscopic decision room, taking in clues and making a highly disciplined guess. It is all part of one beautiful, unifying loop that snaps reality into focus. Think about it. Reality becomes numbers. Those numbers become a transformation. That transformation becomes a decision. And then, the most crucial step of all, the feedback becomes an adjustment. This continuous, structured loop is the literal heartbeat of modern artificial intelligence. So whenever AI starts feeling impossibly complex or scary, just return to this pipeline. Don't worry about the billions of parameters. Think about the basic structure. Input goes into math, which makes a decision, which uses its own error for improvement. The entire sweeping, complex system of AI is built entirely on the simple, intuitive concepts we just walked through. It is just structured mathematics operating in a loop. So the math that used to look like a giant, intimidating brick wall is actually a bridge. Calculus, derivatives, optimization, they aren't locked doors anymore. They're just the practical tools that turn a clumsy mistake into a highly meaningful adjustment. You finally understand exactly how machines learn. So the only real question left is, now that you understand the mathematics of intelligence, what will you build?